All right, let's dive in. Today, we're talking about a piece of nuclear technology that's pretty wild. It feels like something straight out of the future, but it was actually invented at the dawn of the atomic age. And now, it's making a comeback with a massive promise: a future with safer, cleaner, and way more abundant energy.
So, what's all the fuss about? Well, it starts with a pretty bold claim. Imagine a nuclear reactor that, just by the laws of physics, can't melt down. I mean, it's physically impossible. That is the core promise of what are called thorium molten salt reactors, and it's the reason this old idea is having such a huge comeback.
But here's the crazy part. This isn't some brand new idea, and to really understand why it's suddenly back in the spotlight, we've got to look at why it was shelved in the first place. It's a fascinating story of a brilliant technology that got sidelined by politics.
So check this out. Back in the 1960s, scientists at Oak Ridge National Lab in the US actually built one of these things. And it worked. They proved the concept. So why did they stop? Well, in a word, bombs. By the 1970s, the Cold War was in full swing, and the world decided to go all in on uranium reactors because they produced plutonium as a byproduct, perfect for nuclear weapons. Thorium got pushed aside. Now, of course, our priorities are totally different. We're worried about climate change and energy security, so that old Cold War thinking has been completely flipped on its head.
And a huge reason for this second look is just how much of this stuff there is. Thorium isn't just another option. It is incredibly common. It's about 3 to 4 times more abundant than uranium. We're talking about enough fuel to power the entire planet for thousands of years. It's a real long-term solution, which is why even the International Atomic Energy Agency is pointing to its huge potential.
Okay, so how does this thing actually work? It might sound super complicated, but the basic ideas are surprisingly simple and honestly pretty elegant. Let's break down the science of turning this common metal into a powerhouse fuel.
It all starts with thorium-232, the stuff you dig out of the ground. On its own, it can't create a chain reaction. It's what scientists call fertile, not fissile. But once it's inside the reactor, it absorbs a neutron. Then, over about a month, it goes through a couple of steps and transforms into uranium-233. And that stuff is an amazing nuclear fuel. So the reactor literally breathes its own fuel as it runs.
And this is where it gets really different from a typical nuclear plant. Forget those solid fuel rods you've seen in movies. In a molten salt reactor, or MSR, the fuel is dissolved directly into a liquid salt. It creates this hot, radioactive fuel soup that flows through the reactor. And that liquid state is the absolute key to all of its game-changing safety features. It really all boils down to one word: pressure. A conventional reactor is basically a giant high-pressure cooker. We're talking 150 times normal atmospheric pressure just to keep the water inside from turning to steam. That massive pressure is its biggest weakness. But MSRs use salts that only boil at incredibly high temperatures, so they can just run at normal, everyday atmospheric pressure. There's no pressure buildup, which means there's no risk of a steam explosion. If it ever leaks, the salt just spills onto the floor and freezes solid.
And this leads to my favorite feature, which is just pure genius: the freeze plug. At the bottom of the reactor, there's a drain pipe. It's blocked by a plug of salt that's kept frozen solid by a small fan. Now, what happens if the plant loses all power? The very thing that doomed Fukushima. Well, the fan stops. The heat from the reactor naturally melts the plug, and the whole core of liquid fuel just drains by gravity into separate holding tanks, where the reaction just stops, all by itself. No pumps, no computers, no people needed.
So you see, this isn't just a small tweak. It's a completely different philosophy on safety. A conventional reactor uses active defense. It relies on a whole web of complex pumps and backup generators to actively fight against a meltdown. An MSR, on the other hand, is built on passive safety. A power outage, the absolute worst-case scenario for an old reactor, is the very thing that triggers the safe shutdown in an MSR. The laws of physics do the work for you. It's designed to fail safe, not to be saved.
With features like these, it's really no surprise that this technology has kicked off a brand new, high-stakes global race. So let's take a look at who's actually leading the charge to build these things.
And right now, it is not even a close race. There is one clear leader: China. Their progress has just been staggering. They took that 1960s theory and turned it into real 21st century hardware. Their experimental reactor isn't just up and running. As of late 2025, they've already proven it can breathe thorium into uranium-233. And, maybe even more important, they've demonstrated live refueling, which is a massive breakthrough. It means the reactor can run continuously without ever shutting down.
As you can imagine, China's success has created a huge Sputnik moment in the West. The U.S. response has been pretty fast. A recent executive order basically said the country has been held back by over-regulated complacency, and the new goal is to unleash private innovation. They're setting up fast-track programs to help the private sector cut through the red tape and catch up.
And then you've got Europe, which is, well, it's kind of a mess strategically. On one hand, you have its biggest economy, Germany, and their government has flat-out banned any new nuclear development, period. But at the very same time, the wider European Union is pouring money into MSR research and is planning to increase its nuclear power by 2050. It's like the left hand doesn't know what the right hand is doing, and this division is causing the whole continent to fall behind.
Okay, so with all this excitement, it's easy to get carried away. It sounds like a miracle technology. But whenever something sounds too good to be true, it's probably a good time for a reality check. Let's separate some of the biggest claims from the hard, complex truths.
This is probably the #1 thing you hear about thorium. The argument that we can take nuclear waste that lasts for hundreds of thousands of years and shrink that timeline down to just a few centuries. I mean, if that's true, it's a total game changer. But is it really that simple? Is it true? Well, like with pretty much everything in nuclear physics, the devil is in the details. And the answer is a lot more nuanced than the slogan would have you believe.
So here's the catch, and it's a big one. That 300-year number, it only applies to the ash of the reaction, the stuff called fission products. It completely leaves out the unspent fuel, the uranium-233, which has a half-life of nearly 160,000 years. So here's the real insight. The waste advantage doesn't come from the thorium itself. It comes from the Molten Salt Reactor system. It's the reactor that can keep recycling and burning up that long-lived fuel until only the short-lived stuff is left. The magic is in the machine, not just the rock you dig out of the ground.
Okay, on to the second big myth, that thorium reactors are proliferation-proof, meaning you can't use them to make nuclear weapons. The logic here sounds really solid. The U-233 fuel it makes is always contaminated with another isotope that shoots out incredibly deadly gamma rays, making it too dangerous for anyone to handle. But remember that liquid fuel soup? Well, it creates a very sneaky backdoor. Remember that intermediate step, protactinium-233? It turns out that's a completely different chemical element, which means you can continuously filter out of the liquid fuel before it has a chance to turn into that super radioactive uranium. You just siphon it off, let it sit for about a month, and it decays into perfectly pure, weapons-grade U-233 with none of that dangerous contaminant. So, paradoxically, the very liquid fuel that makes these reactors so safe also creates a new and very serious proliferation risk.
So, given all these complexities, what's the actual path to getting these reactors built and running? Right now, the industry is split, and it's placing two very different bets on how to get there.
In one corner, you have the purists. They're going for the whole shebang, the true liquid-fueled thorium reactor. This is the design with the biggest potential payoff, but it also has huge technical hurdles, like finding materials that won't get corroded and destroyed by the hot, radioactive salt. In the other corner, you have the pragmatists. They're taking a hybrid approach, using proven solid fuel but cooling it with molten salt. It avoids the biggest technical challenges, which means they can get to market way, way faster.
And if you're wondering who's winning right now, it's the pragmatists. And it's not even close. A company called Kairos Power already has a construction permit for its demo reactor. They've logged thousands of hours of testing. They even have a major customer lined up. Google wants to use their reactors to power data centers. By avoiding the liquid fuel problem, they've sidestepped the hardest challenge and are now years ahead of the competition.
And this leaves us with a final, huge question. The race is truly on. So, is the next chapter of nuclear power going to be written by these fast-moving, pragmatic engineers in the private sector who are building hybrid reactors to get us off fossil fuels faster? Or will it be defined by state-sponsored visionaries like in China, who are patiently playing the long game to unlock the ultimate potential of a true thorium reactor? The answer to that question is going to shape our energy future for the next 100 years.